Good. So what do you got today?
We moved on into like defining 3D shapes and determining the surface area of 3D shapes, like
Okay.
prisms and pyramids and
It
stuff.
sounds like chapter 12, surface area and volume.
Yeah, probably that one. I think it's chapter 11 in our books.
Oh, chapter 11 in my book is area of polygons and circles, which is what you just finished, right?
Yeah, just finished that.
Okay.
I believe I got an A in that test. So.
You got an A in that?
Yep.
Good for you. All right, so exploring solids. How far in are you into this chapter?
Into this chapter? Not very far. We just started it today.
Started it? Okay. Let me go to the start in my book. Do you have anything you can send me?
I do have that back downstairs.
Do you have your homework or anything that you need doing?
Yeah, I do. Come on.
Why don't you grab it?
You just I can always grab my backpack.
That's always the better way to go.
Yeah. Well, I'm not with you.
Now, see, if you were on the trimester semester or system, you'd be off today.
Yeah, holy. All right. There's one coming your way.
Okay. Just got an Uber. Sure didn't come through as a spam. There's another one. All right, let's have a look. Okay, yeah, this is, in fact, I think I have a page that looks exactly like this. Yeah, not totally, but close.
And that comes in there.
All right, let's blow this up a little bit. See what we got on it. Where are you supposed to start on this? Which one?
Number three.
Okay. I'm not particularly strong on naming polyhedrons. The only thing we can tell about number 3 is that how many sides does the base have?
5.
And that's going to mean, since it all goes to a central vertex, we got to have 5 faces also.
Mm-hmm.
So I'd be inclined to call that what?
Pentagon pyramid.
Okay, good. Yeah,
Pyramid.
I think that's correct. There may be a special word for it, but a pyramid is basically where it goes to a central point regardless of how many sides the base has. In other words, the base could have 3. It could be a triangle, which I believe is called a tetrahedron, or any number of sides on the base. Determine whether the solid is polyhedron. There is something, the one type of polyhedron that you're going to get into a lot are prisms. Number 4 is a prism.
The hexagonal prism.
Yeah, why is it a prism? In other words, there's a certain quality that all prisms has 2 equal opposite bases. Equal, opposite, and parallel. In other words, the top is the same as the bottom, and they are parallel. What's that? Number 5. To the prism, I guess, is my question.
I don't know. I don't think it's polyhedron.
Is it a prism?
No.
Well, actually, look at the back side. It's equal, opposite, and parallel to the front side.
Oh.
That makes it a prism by definition. I don't know whether it's a polyhedron. I'm not quite sure what the definition of polyhedron is. I think it is. A polyhedron is a solid that is bounded by polygons. So I guess this would not be a polyhedron. But it is a prism. Now, how do you find the volume of a prism?
Length times width times height.
Actually, if you take the area of the base, let's look at number 4.
I have the formulas written down. I don't know what I was doing.
If I take the area of the base, what do I have to multiply it by to get the volume?
Height.
Height, exactly. Now, if you look over here at this regular polyhedron, or not polyhedron, where it comes to a point, what's going to be the difference of this volume compared? How do I find this volume? Perhaps I'm getting ahead of myself. Well, here's what happens in all cases. Let's say I have a right cylinder, soup can. Okay, that's a prism, right?
Mm-hmm.
In other words, it's a prism because the top and the bottom are both circles, and they're opposite one another, and they're parallel. So if I want the volume of that, I'm going to take the area of the base, and I'm going to use a capital B for that to distinguish it from a linear measurement, which is a small b. Okay? In other words, if I have a rectangle and I want its area, this is base, that's height, I take base times height. Well, with a prism, you take base times height also, but the base is an area dimension. It means it's in square inches. So if the base is in square inches and the height is in inches, we end up with cubic inches. You always want your volumes to be cubic inches or whatever, cubic whatever dimension they're using, and areas to be two-dimensional, and measurements of linear things to be one-dimensional. In other words, in the last chapter, we tried to figure out what the measurement of an arc was. Okay, this measurement from there to there. That's one-dimensional. In other words, if that was a piece of string, I could cut it right there and straighten it out and measure it with a ruler. So this is standard for all prisms. It's the area of the base times the height. Now, if I take a prism and I don't make a right cylinder, but make it go to a point like a cone, what's the volume of that cone? And whether you've learned this or not, this is coming up. So it's not going to hurt you to cover this. And it's coming up in this chapter. It's always 1/3. No matter what the base is. In other words, if I draw a square as the base, and I make it go to a point like that. So this thing has 4 lateral sides. The volume of the, I can't draw worth anything, but you understand what I'm trying to draw here. It's like a right cylinder, only it's got a base of a square instead of a circle. But it goes to a point. When you go to a point, the volume is always 1/3 what it would be if, as opposed to if this was a rectangular brick. In other words, if this went straight up like that, the volume would be base, the area of the base times the height. It would be a prism, right? In other words, if I had an object that was like a rectangular brick here, I would take the area of the base, multiply it by the height. That's this formula here for all prisms. Whether the base was a circle, a square, 5-sided, 18-sided, it wouldn't matter. I would just take the area of the base times the height. Well, now, if you had a piece of sculpture, let's say you had a piece of marble that was shaped like this rectangular brick, you came in and you wanted to turn it into this thing, you would have to shave away 2/3 of the material. And so when I look at this object, it's going to be 1/3 the area of the base times the vertical height. The vertical height is not the same as the slant height. Okay, slant height is usually labeled like that, lambda. And that would be the height from there to there. The vertical height is if you drop a dotted line directly to the center such that it makes a right angle with the base, that's the vertical height. And that's what you have to figure out a lot of times when you're solving these solids. And the other thing let's talk about is surface area, because that's the other thing this chapter is all about, is surface area. When you're figuring out surface areas of these solids, you basically just have to count up every one. In other words, if I make a rectangular solid, and I want to know the surface area of this footlocker, suit, or chest, or whatever you want to call it, over here on the right. How many faces does it have?
6.
Just figure out the area of each face. So it ends up that not only is it 6 faces, but it's a prism 3 times over. In other words, that side has an opposite and equal side, that one does too, and so does that one. So this is definitely a prism, and if I want the surface area of this, I would take 2 of those, 2 of those, and 2 of those. In other words, I just have to figure out each surface area, multiply it by 2 because it has an opposite side. If I want the surface area of this thing over here that I've drawn, then I only have one base to consider. So I need to take the area of that base plus the area of each face. There are 4 faces on this particular object here, pyramid. Like I said, I'm not real good on names. Your book doesn't help that much. Have a look. What else is? Okay, 12.1. Skill practice. Gotta have this same page. No, it's interesting. Books are not that similar. All right, and number 6, why is that not a rectangular prism?
Because the 2 bases are triangles, not rectangles.
Okay, you know how to draw a rectangular prism?
Mm-hmm.
It's what I call a brick. A triangular prism?
Yeah, just triangle.
It would be like number 15, only instead of going to a central vertex, it would just go straight up, starting with a triangle as a base. Square pyramid. That's what that's called. Number 16 is a square pyramid. And a pentagonal pyramid.
That was number 3.
Or 4. Oh, no, you're right. Number 3 is a... So if it goes to a point, it's a pyramid. If it doesn't, it's a prism, pretty much. Euler's theorem to find the value of n. Okay, hold on a second. Let's... Euler's theorem. This is one you don't hear very often. In fact, I got a ton of geometry students, and I rarely hear Euler's theorem. So it's not an easy one. It's the number of faces plus the number of vertices equals the number of edges plus 2. So if I look at number 11, they're giving me the number of, they want me to figure out the number of faces. So how am I going to figure out number 11? Using Euler's theorem. What am I going to fill in for F? Let's fill in something for each of these. F, V, and E. F is N. V is 12. E is 18. So the number of faces is what?
8.
Okay. And that's all you're going to do in each of these problems. These are pretty easy. This isn't hard at all. It's just, I don't come across it very often. I suppose you don't come across it very often because it doesn't really have much practicality. I mean, I guess if you came, you were walking in the desert and you came across something in the desert and you wanted to know how many edges it had and you could count the number of faces and vertices, okay. But this is not terribly practical and doesn't really present any problem. As long as you start with this theorem and plug in your unknowns here, they're giving you 2 out of the 3, F, V, and E. Okay, so for 15, let's just make sure that it's right. It's always nice to... How many faces do we have on 15?
3.
How many vertices do we have?
4. So you'll have 5 edges.
Let's count them. 1, 2, 3, 4, 5, 6. Where did we go wrong?
I don't know.
Number of faces is not 3, it's 4.
Oh. Oh, I didn't have to.
Because of the base.
Yeah.
In other words, you're not just talking about the lateral number of faces. You're talking about, if you picked this object up and turned it around, that would look just like a face. Wouldn't be any different. It's triangular. It's just not on the bottom. So let's check 16. How many faces does 16 have?
5 plus 5.
So it should have 8 edges, right?
Mm-hmm.
Well, we got 1, 2, 3, 4 edges there, and 1, 2, 3, 4 edges there. How many faces does 17 have?
5.
Correct. Is 17 a prism?
Yes.
Because that is equal to that. And you could figure out the height or the volume of 17 if you knew the area of those equal and opposite bases. Then the volume of a prism is always the 2 times the area of the bases plus the area of the lateral faces. So if I wanted to know the volume of this, I would need to know the volume of that triangle, the area of that triangle, multiply it by 2. And then I would add to that this square-looking base plus this lateral rectangular face plus the lateral rectangular face on the other side. So to get the volume of prisms, you just add up the 2 bases and all of the lateral shapes. '18 is going to be pretty easy with regards to this question. So will 19. One that looks kind of interesting is 20. So does 20 fall under Euler's theorem? The number of faces of a polyhedron. Well, is 20 a polyhedron?
I believe so, because it's
Well, here's the definition. A polyhedron is a solid that is bounded by polygons. Well, that certainly is, number 20, called faces, that enclose a single region of space. That's true. That number 20 does not enclose multiple regions. It's not like 2 spheres next to one another. that would enclose multiple areas of space. So two spheres would not represent a polyhedron, but this does. This is probably a convex polyhedron, I'm guessing.
Yes.
There's going to be concave and convex. Hold on a second. Wow. Oh, just a second. They don't really talk about convex polyhedrons. They talk about convex areas and stuff. But okay, so let's apply our rule to number 20, Euler's theorem, and see if it works. How many faces do we have? Oops, hold on. How many faces do we have here?
8.
Let's see. Back and front, or the front of that and the back of it is 2. Looking from the top, we see 3. This one, and the bottom one. That's a total of 5. And then we have 6, 7, 8. I see 8.
That's what I said is 8.
Okay. Sorry. In the process of counting them up, I lost track of them. How many vertices do we have? Probably the easiest way to count the vertices is from looking from the top down. If I'm looking from a bird's eye view at this shape, I see four vertices there, I see 4 vertices there, and I know there's 4 at the bottom. Are there any others?
I don't believe so.
I don't think so, not that I can see. So that's 12. So there should be 18 edges, because we take the number of edges and add 2. So let's see. Do we have... What's going on here? I don't think we're going to find 18 edges here? Maybe. Well, we got 4 on the bottom, right? Got 4 there. Got 4 there. That's 12.
And they've got 3 on each side.
Yeah. That's 18. Where are you getting 3 on each side? Let's see. I got 1 edge there. I got 1 edge there. I got 1 edge there. Did I count this one? No, I got 4. Maybe I missed a vertice.
I don't think you did.
The number of edges. Okay, there's 4 edges on the bottom that are different from the 4 edges of that middle layer, that are completely different than the 4 edges of that. So that's a total of 12 edges.
What if there's like 2 vertices, like, what if like in the middle, like where it's the crease there? What if those aren't vertices?
Well, that would be oh, you mean maybe that's not a vertice there?
Yeah.
Well, I think we need more vertices, not less, because we're going to end up with more edges than 18. In other words, we got 4 edges in the, if we look from bird's eye view, we got 4 edges there, 4 edges there, and 4 edges there. Now, if we look from this direction, I see an edge there that's different. 1, 2, 3, you were correct. I cannot count that as an edge, number 4, because I already counted that. So on this side, there's only 3 different edges. There's that one, and that one. Same 3 edges on the back side, and that's all there are. So there really are 18 edges, 12 plus 6. That makes everything right.
Mm-hmm.
All right. I don't know why geometry always does this. It seems, I don't know. Seems to me every single chapter starts out with obscure stuff. And then it gets into the meat of the stuff that you need to know. You're never going to get a question regarding Euler's theorem on the ACT test. Just not going to get it. That right there, you do not have to know that. But for geometry, you do. You will get lots of questions on the ACT test of surface area, of polyhedrons and prisms. So you do have to know all about surface area and volume. But this thing about edges, that's a little obscure. All right. By next Monday, you'll be into the meat of this chapter. You'll be calculating surface areas and volumes galore. All right?
All right.
All right, Cole. Well, keep up the good work. Sounds like you're doing good.
Mm-hmm.
All right. Talk to you next Monday.
Talk to you next Monday.